Luc Steels, why is it so hard for a human brain to come up with something like language?
Well, there are many reasons. I think that language is probably the most incredible thing that we do with our brain. And there are no other species who have language. And so one reason is already that in language that everything comes together. You need to perceive the world in order to speak. You need to conceptualize the world to impose a kind of framework of concepts and perspectives on the world. You need to take into account your listener, the context, and then of course you have syntax, you have grammar, you have your lexicon. Speech is very fine-grained motor control, enormously complicated, also listening. So it's sort of the ultimate of what we can do with our brain. So that's one reason why it's difficult for humans, I think, or for, let's say, biological brains, but it's also extremely difficult for artificial brains.
We'll talk about that. Just stick a moment with the human brain. So, since when do humans speak?
Well, that's a very controversial topic. I mean, if you would ask 15 years ago, there was a sort of consensus that maybe 40,000 years ago, because there was the explosion, the cave painting that was found in south of France and so on. But since then, the date has been progressively moving backward. And so now everybody agrees that, when humans went out of Africa, there must already have been language. And in Neanderthals, where before they were thought no language, now everybody believes they do. And so it's going back and back in time. So I don't know, some people now talk about maybe 1 million years ago.
But how do you estimate this?
Well, they estimate this in terms of indirect evidence. For example, the use of symbols, which is one of the key aspects of language. So, for example, they have found from 120,000 years ago already the use of ochre and for painting body and faces and use in ritual contexts. So, and there's also the argument of the brain itself, and the vocal cords and so on, the vocal machinery. I mean, there's no reason why Neanderthals would not be able to produce enough sounds to create a language. And also the brain hasn't really, made a big leap 40,000 years ago or even 120,000 years ago. So, so I also believe that it's actually very, very old. It's part of our species.
And what happens in our brain when we speak and when we learn a language? How does the brain itself does language?
Well, we do not know at all what goes on in the brain. I mean, what we know about the brain today is just, I would say, nothing. And there's now neuroimaging. There's a lot of progress in that area, so we get a lot more data. But the data that we are getting is not telling us very much, actually. I mean, just imagine that you come from Mars and you see what we are doing with computers here, right? I mean, if you would just investigate that computer, you would measure certain things of the physics of the computer. I mean, it would teach you very little about, let's say, why the World Wide Web, how it works, or why, this computer is able to do the software of the machine, right? And so just by looking at the hardware and measuring things is giving some insight into neurobiology, but is giving us very little insight into actually the design principles and the main mechanisms that are underlying things like language.
But nevertheless, since now you described how hard it is for the brain to come up with language, how little we know about how it's actually done in the brain, but nevertheless, you as a computer scientist and linguist, are trying to produce something like artificial language, robots, creative enough to come up with their own language. How
Yeah.
do you do that?
Yeah, well, I think the approach of artificial intelligence is indeed to not to look so much at the brain, but to look at the problem from a kind of top-down perspective, right? And to say, what do we need in terms of computational processes to see, for example, the emergence of language in a group of robots? I mean, this is like what, you know? How
There's
can
only the robots, and they come up with the language
Yeah,
themselves.
that's right. That's the target of our experiments. Now the question is, what do we have to put into those robots? It's not the case that they start from scratch, that's for sure. So we already put in a vision system, motor control. You know, there must be a layer of sensory motor capacities which is already there, like developing in the child, you know, the first years of age. But then on top of that, we put strategies, which are ways of doing things, you could say, for forming new concepts, for example.
Software,
Yeah,
written
software.
in concept.
That's right. So
software,
they are
yeah.
like programs,
Uh-huh.
little procedures that allow the robot to play a game, so to go through a script, to make new concepts. So the way of making new concepts is by introducing distinctions, inventing new words.
Just stick a little
Yeah.
more with the concept. What does it mean to make new concepts?
Well,
and
suppose we look at color and at distinction between red and green. Okay, so how do we do that? Well, we perceive the colors, you know, very much like a camera, in fact. So we get all these bits of information, and they are mapped into what we call feature spaces. And so maybe, you know, you know about these the color cubes and the color space, right? Which is an old thing already, like Goethe and all these people have looked at it. So you organize all these points in the color space in terms of a two-dimensional, three-dimensional, or whatever n-dimensional space. And a concept is actually a region in this space. So the points that are close together form a concept. And so learning a new concept is like cutting a region of that space.
Categorizing your
Yes,
environment.
exactly. And being able to say, okay, that point which I see there is close to the prototypical example of the color, you know, and that is close to the prototypical cloud or
okay, but
green.
Once a computer has distinguished, say, the red dots from the green dots, it still doesn't know, or it still hasn't come up with the name red.
That's right. So the way that this is going on is in our experiments is they play a language game. And so there are, for example, red and green and blue objects on the table. And I'm the speaker, and I want to draw your attention to one of the objects. And so in order to, using color, let's say, in order to do that, I must have a distinction. Okay, that's one with this color space. But then I must have a word. Now, suppose I don't have a word. So then this robot is going to invent a new word, like make a random combination of syllables. You know, like badoba or movamo, or just random combination. And so thinks up a word and then says it to the other robot. Okay.
Thinking is random.
Yeah,
Is
randomly putting together.
get the syllables. Okay.
So we give it a repertoire of consonants and vowels, and then just random combination.
Okay.
There's nothing intelligent about that part. And then the robot creates this combination and associates that with these points in these spaces. Okay, and so the speaker, robot speaker, has invented that and stores it in his memory, and the listener hears the word, let's say, bomavo. Bomavo, what could that mean, right? And then the speaker points to the object in the world that is the red object.
The bomavo.
The bomavo that he created at that point. And this way the listener can learn about that word in this interaction. And so, of course, it could be wrong, they could guess the wrong meaning or something like that, but still, he gets a lot of, by pointing, I constrain enormously the meaning of that word, what it could be.
And the likelihood rises he
Yeah.
gets the right thing.
Yeah, because it's about an object
Mm.
which is there, right? It must be relevant for that object. And so this is one way that a word can jump from one speaker to a hearer. And then, of course, this hearer will talk to somebody else. They also play a game. And so what we do in our experiments is we create populations of robots. And so it's not just one or two. You know, we can have many robots, and we do. And then they, some robots are here, some robots are there. You know, they invent a word, they invent a word. And they talk to each other, and those two talk to each other. And so progressively, you get coherence in this population. Not immediately. In the beginning, you see lots of variation, like in human language, in fact. But because they talk to each other, and after every game, they will adjust their internal memory to be more similar to the one they're speaking to or listening. And so, you know, if I say, let's say, blue, right? Okay, and maybe for you this was not really blue, but some dark, maybe closer to black.
Mhm.
Okay, but then if I say blue, you learn now what I mean by blue, and you can shift your prototype a bit in the direction of what you're seeing. Not completely, but you adjust to some extent. And so this kind of alignment where every individual, you know, we call them agents, if they interact with each other and then not only kind of in an autistic way stick to their own inventions, but also align, adopt, try to figure out what the other one is meaning, and so progressively they arrive at the shared communication system.
And how far have you come so far? I mean, what if I go to your laboratory and switch the turn on the system? What do I hear? What do I see?
Well, if you go to the laboratory, in fact, you don't have to go that far, because we installed 2 robots here in the building, you know, and they are playing the game. Now, of course, if you see one game, you don't see very much, because it's just one interaction. You know, it's really, language is a collective phenomenon, right? So you have to look at many agents interacting with each other, and we produce about 16,000 sentences per day, just to give an idea, right? So also here, just one interaction is interesting, is fascinating to see, but then we have to look at a lot of interactions. But you can see the invention of a new word, you know, how a new word is learned, and also, if the robots talk with each other, then you say, well, why do you do that? You know, you get an artificial language invented by these robots, and we don't understand them anymore. This looks like a very stupid idea. But actually, when we get to talk, well, when we start talking with these robots, also playing games with them,
You can, as a human, point to something,
That's
say
right.
something.
Yeah, or show actions and things. Then the language of the robots and the language of the humans are aligning with each other.
So you can teach
Yes, and you can
English
teach
or
them.
French.
Yeah,
or
you can teach them. Now, of course, we do English and French. I mean, 60,000 words, complex grammar. That's not where we are today. But I'm interested in the fundamental principles. And I think in terms of the fundamental principles that we have made really huge progress in the past decade.
It's very interesting. You describe one way of learning a language. So coming up with something, also identifying something, coming up with a random name for it, pointing to it, that way teaching other robots what it is, or what you think, or what the robot think it is, and how it should be named. This is one way. Describe another way they teach each other language, or how a language comes up amongst robots.
Well, another way, I mean, well, the first thing I should say is that obviously, in many cases, the inventions that we make are not totally falling out of the, a totally random new word. That's not the way we do it. We often use an existing word and we adapt it to a new function. Like a mouse, a computer mouse, is because the shape of the mouse in the beginning of these pointers, they were not called a mouse for sure. But you see, we use analogy, we use metaphor. Another thing we do a lot is to coerce words into new functions. For example, you can say, why don't you Google him? Okay, meaning go to Google and look him up, right? But so Google, which was in fact the name of a computer program, became the name of becomes a verb. And so we coerce words that are nouns into verbs, or verbs into nouns, or we stretch constructions and so on. So
a lot of recycling we do.
Yeah, recycling. I mean, it's very creative. For me, language is a totally creative activity. Every time we speak, we mold the language in new ways. And then you have the collective result of all this creativity, which is then a moving target, right? Language is never static and fixed. It's an evolving complex system.
And how do you code this creativity into robots?
Well, by these strategies. So I said the robot makes a random word by combining consonants and vowels. Okay, that's one strategy, but that's a kind of not very exciting strategy, right? Another one, which we can also program, is to say, okay, try to find a word that more or less fits with what you want to say, that has many of the features, and then reuse that word. That would be another strategy. And so what we are actually doing is to try and come up with these kinds of strategies and then investigate what they can do. I mean, how they lead to language creation. And so, for example, agreement system, like, between subject and verb, or in German, between the article and the adjective and the noun. They agree for number and gender and all these kinds of things, and for case. So, if you say, where does the system come from, And then what I would say is we have strategies for using markers that will help to reduce the combinatorial complexity of language. And so we try to figure out what the strategies are and then create computer simulations where we can see that the strategy indeed gives the kind of structures that we find in human languages.
And what since you now doing all these experiments and you coding these kinds of strategies and let robots interact with each other and talk to each other, what have you learned? What was the most exciting thing you've learned so far?
Well, I should first say that the experiments, when you see them and when you do them, they are incredibly moving. I mean, a few weeks ago I showed one clip to a friend, and she said, well, this is amazing. This is like the first time the Wright brothers, you see an airplane going up. And that's the feeling that you have when you work with that. It's something very remarkable, something mysterious, right? Where does the meaning of words come from? How does new meaning arise? Where does grammar come from? So this is kind of the excitement that I want to share about these kinds of experiments. Of course, you have to take your time to really understand what is going on. It's not like an airplane which you can see, but still. So this is one thing. But the second thing is, in terms of learning, is really the power of cultural evolution. And so before, when people studied language evolution, they very much thought about a genetic component, like an innate structure in the brain, some mutation, a language gene or something like that. And so they put
that leads to the evolvement of language.
That's right. That of course we need the neurobiological apparatus to do language. There's no doubt about it. But to me, the great action is in the cultural level. And so these processes of cultural evolution, which of course is not just language, it's also tool building or political structures, all of these kinds of things. So I think now through this research we have an insight in what the principles are. And the principles are very similar to biological evolution, namely selection, variation, recombination, reuse of materials. But they are happening at the cultural level. And the criteria are not survival and having enough offspring, fitness, biological fitness, but they are, communicative fitness.
And do you like the phrase meme for that?
Yeah, you could. Well, memes is another way to think about it, but I think that the theory of memes has many of the right features, but was never developed to a point where you could actually do scientific modeling, or computer simulation. So it was an idea of Richard Dawkins, and a very good idea. But, for example, there's already the analogy between genes and memes is kind of not exact, right? Because genes are being copied, really copied from one to another, whereas our thoughts, our grammar, our words, they are not copied, right? We have to reconstruct them. So the process of transfer, I don't like transfer, it's really reconstruction by the learner of what might be meant, what might be the concepts that the speaker had in mind. And so this reconstruction process is very different from the copying. Of course, there can also be errors, that's one difference, but also I believe very much in the creative potential of humans, the problem-solving capacity. It's not just a model of random search or no, we are intelligent, so we try to solve problems. And in language also, when we cannot explain something, when we cannot say something, we will invent other ways of saying it, right? So it's this creativity is what is important.
And since, another question first, what kind of applications do you see? Do you deal with this kind of thought, like, okay, it's very interesting, very fundamental research, but once we've reached our aim, our goal, it might be possible that, I don't know, robots teach in schools, or I don't know. What kind of applications do you have?
No, I don't. Well, maybe they teach in schools of other robots, but I think humans should teach in schools. No, I think there are many applications actually. One of them is that suppose that we send a colony of robots to Mars. I think this will happen at some point. Then the question is, how are these robots going to communicate with each other, and maybe with us, but also with each other? Now, the robots will have different sensors. They will encounter new problems that we have not foreseen. They need another way to, deal with their environment that we cannot even imagine, right? We don't have the words for it, for sure. And so that's part of the idea that if you have real autonomous groups of robots, colonies going to Mars or maybe underwater or whatever, that they are intelligent enough to be able to expand their own capacities for communication, so that they can deal with open environments, unforeseen problems. And you could also apply it in the software, the web or the virtual spaces. We also have entities that are to some extent independent and have other sensors and other ways to interact with, the virtual world in this case. So I think that's one of the application areas. Now, I think there's also other application areas, because for me, language is an evolving system, human language. And so what does not work is that we take the existing human language, and then say, okay, we put that in a robot, and then we are done. No, because you turn around and the humans have already changed their language, right? So the language is evolving. So the way that if we want robots to understand us to some extent, or that we can talk to them in our way, then they will have to adapt and be able to to follow this evolutionary path of human language. So I firmly believe that it's only with this kind of methodology and this kind of research approach that we're ever going to have robots with which we can reliably communicate in human language.
And this scenario described, sending a colony of robots to Mars, solving their own problems we don't know yet, developing their own words, their own language for the problems. There's definitely intelligence involved. And of course, do you think, I mean, you devoted an opera to this topic, do you think that an opera you wrote yourself, do you think that there will be robots that are more intelligent or as intelligent as people are?
Well, I'm extremely skeptical about all this talk today, you know, about the singularity being in 2040, something like this, that robots are going to take over the world, all these kinds of scenarios. I mean, our intelligence today is so far beyond what we can even imagine, you know, in terms of complexity. I mean, and it's by building actually that you discover that vision, let's say, just seeing the world is an unbelievably complex process and a living system. It's a bit like biologists who discovered that, you know, there are macromolecules and doing all sorts of complex chemical reactions in our body. I mean, once you're aware of it, you are amazed that we could still live, right, with all this complexity. And I think for the brain, and particularly what goes on in the brain, not just the hardware structure, but the software structure, you know, is so enormously complex that I don't think we're gonna be able to anytime soon to reach that sort of level. And on top of that, even if we would be able to build systems that are much more intelligent than we have today, I think we will. You know, then we have to think deeply whether this is what we want. It's not because we have the technology that we should do it, right? And personally, I'm fascinated by all these questions, and I think we learn a lot about ourselves. So it's a project. It's almost like philosophical project, you know. But then we have to really think. And even though I work in technology, I'm certainly not at all in favor then of actually putting this so in practice as some people would like to do.
And the last question is, an important part of human beings is morale and ethics. So you have an idea what is right and what is wrong, and you act accordingly. Do you think, since robots are obviously capable of adapting to semantics, to new words, to language, is it possible to say, well, here's a set of rules, these are right, these actions, and these actions are wrong, and by interacting with each other, they adapt these rules and they come up with something like ethical activity. Do you think it's possible?
Yeah, it's a very interesting idea. Nobody, as far as I know, has tried this. But the idea, you said it right, I think, is the adaptation. You see, in the biological world, there's always, in an ecosystem, there's always equilibria between different species. Or within a species, there are, you could say, rules, but of behavior, you know, implicit in the way that the groups of animals are interacting. Why? Because if they would not follow the rules, the species would collapse. So it has grown, and it's partly genetic, it's partly cultural, but there's been time in biology to have these equilibria, and my worry is that, like with the robots, you say, okay, or software agents, you know, we give them the rules. Somebody comes up with the rules. Now, I think that's very dangerous, because we need time to have these rules evolve and be adapted to the situations that they encounter without causing harm, you know, which if robots are too powerful, they might. But of course, the same is true about, let's say, nuclear energy, right? So as we have seen with Fukushima, or I mean, once things get out of hand, they really get out of hand. So we need, for this, we need enough time to balance, to understand this moral and ethical behavior, not just to put it in, which is already good if that would happen, but actually to find this equilibrium, this co-evolution with human societies. And I think we should really be careful and stay, before we put this into any kind of practice.
Luc Steels, thank you very much for coming. Thank you very much for your time and your research. Very interesting.
Okay, thank you very much.
Thank you. Okay. Danke fürs Zugucken. Hast du schon weg? Nee, ne? Genau. Also, Videos gibt's bei DCTP TV und beim YouTube. Mein Name ist Philip Banse. Bis später.